In the earlier video, we learned that actually there is a need to measure the sky, the contribution per pixel inside of the source aperture radius, so that we can eliminate the contribution from the unwanted count from the sky or background. But the pixels that actually included inside of the source aperture, there is no way that actually for us to distinguish this fraction of the count for this pixel is truly coming from the target, but actually this fraction, such as 10%, are actually coming from the back. We are simply recording the sum of two origins per pixel. There is no way that actually there can this origin. So how do we actually measure the average eye contribution per pixel inside the aperture? We need to actually rely on certain assumptions. One is in an ideal situation, eye contribution is not changing, depends on the viewing direction. So meaning that actually that this part of the sky versus that part of the sky contribution is the same. Meaning that actually the sky is copied. And uniform means that actually the, the underlying the structure. Then by using one of these two common the approach, so we can actually calculate the the per pixel sky contribution. One is using the two the different size concentric circle they placed on the centroid. So this case, the actually innermost blue circle is this aperture, source aperture. Then some pixels away, there's a gap between the source aperture and the inner sky radius. So that inner sky radius is chosen in such a way that actually it is not close to the target, so that actually that count coming from this target is not really included. So actually safely exclude most of the. So that's the selection criteria for the inner disk, inner radius. Outer radius is chosen in such a way that actually that there are enough number of pixels that actually included in the sky annulus region, but not large, so that actually contains the background noise, such as like this unrelated star. So for the once that actually sky annulus region is defined, then we want to actually calculate some representative sky pixel value. How do we do? There are three possible methods. Actually, one is the simple arithmetic mean, which is bad because actually if we do the arithmetic mean and when there is the unrelated background source are actually included, then this count from this background star is actually biasing or skewing the true average sky. The mean is the bad way. So oftentimes that actually we are using median and then mode. Median and then mode are actually very similar, and if the distribution of pixel values are actually symmetric around the mean or value or peak value, the median and the mode should actually result in the same value. But if the distribution of the pixel values are actually skewed, asymmetric, then the peak value, most frequently appearing the value, is the mode. So mode is that value, and in that case, actually the median should be slightly shifted to the higher value because of this the prolonged tail in the higher. The median is then if the the sky annulus region is actually oftentimes more the used method because that actually even in the case that actually with the slightly changing sky background, sky region was chosen close enough to your target so that actually that the sky average sky count contribution per pixel is close enough to the true the sky contribution instead of the source aperture. If the observing field or your target is actually showing in such a way that that over a reasonably large size of sky, such as few times the field of view of your observation, the sky is actually basically uniform, then you can actually the designate that actually certain area free of any background source, such as like this rectangle or square, and calculate the median or mode of the sky pixel within this dedicated. But then I think that there are some cases that actually that this approach may actually not work, such as like this. So your source, when science target is embedded in a rapidly changing background, such as this supernova explosion. They explored the supernova in 2004 in the spiral phase one spiral galaxy 74. How do you actually measure the background contribution in this source aperture radius? For this, for this supernova explosion case, oftentimes you have pre-explosion image, or maybe that actually a few months or years later, when the supernova actually decayed sufficiently, you can actually calculate, take the another image and then calculate that actually that the location, the sky, the contribution at that aperture, source aperture, that can actually solve the case. But it's not always the case. And when your science field is really crowded like this, or have non-uniform structure, is the molecular the cloud. And what if that actually you are trying to measure this the brightness of this particular object? It has crowded the background source nearby, and then some sky structure. In this case, there is no true that actually idealistic the, the method. But actually, the best that actually we can do is borrowing the power, PSF fitting. So from this observation, or maybe some other calibration observation, you actually determine the really high quality the PSF, and this PSF is fitted to each recognized the source in this field. This can be the tens of thousands that actually PSF is being fitted. That for the realistic, I think the for exemplar case, let's consider this. So this is the crowded field, and you feed it PSF to each one of these recognized the point source, including these four the red circled ones. Then once you actually fit the scaled PSF for each source, you subtract rigid, then that can actually subtract it out all this point source and then leaving behind nice the sky the background region. And in this sky region, you notice that actually there is this really around the bright sort of the brightest star, like this four plus that actually this one, there is a large residue, meaning that actually that apparently that pH thing is actually quite poor or stuff. But there is not PSF fitting accuracy precision is proportional to the source brightness. The brighter the stars, actually the PSF fitting works best. The PSF fitting is actually really robust. And why that actually these are suffering from residual? This is the prime example of Poissonian noise. Remember that actually Poissonian noise is proportional to the square root of the source. So really bright star, actually Poissonian noise is larger, right? Then this Poissonian noise is fluctuating for PSF fitting. So that your subtraction, I think PSF, although that actually PSF was really good and high quality, because of the is fluctuating, can actually, or you oftentimes see that large residual around nonetheless, when you actually do this PSF, the subtraction of each sources in your field, you can actually have nice, much better improved sky vision. Then either that actually you define the source sky annulus region or maybe dedicated sky region, then calculate the median or mode of sky contribution. You can actually nicely average sky